Okay. The sign-in sheet's gone around. Has everybody had a chance to sign that? Okay. Okay. So, okay, the screen's on. Okay, so I've got RAM pulled up. Before I move into this, is there any RAM-specific questions? Like, have you all installed it and started messing with it? I hope. Like, let me say this. Whether you haven't installed it, I'm kidding. Not really, no. Everybody should have RAM installed, just regardless if you're working on it or not. This is a really fun, really cool, nifty program. Let me say this. When we meet, whether or not it's Wednesday or Friday next week, I'm fine with your decision, but I do not want to come back next week and find, oh, we still haven't opened it. Like, just don't bother coming. I mean, you really need to at least have it downloaded, have it installed, and start the process of building your frame. Okay, just seriously. Now let me recap what we left off with last time. And last time we built a really rudimentary frame. I'm probably going to modify some things slightly to give it a little bit more reality. So if you recall, if you go into the model component, we did a floor beam or a floor framing plan. And we have a dead load on there, but we didn't put a live load. I do want to show you that. So if you go to prop table, we created a decking, if you remember. So we have a floor slab that's 3 inches thick above the flutes. The studs are 4.5 inches long, and so on and so forth. We did that, but we didn't do a live load. So let me show you a live load. So if you go to layout, or no, sorry, if you go to prop table and go to loads, you have surface loads, line loads, point loads, and you have snow loads. So pop quiz, where would the line loads pop up in this structure? The perimeter, the walls. So you'll make sure you'll want to specify that. Now for surface loads, these are pressure loads. So, did I show you this? I think I did show you this. Okay, but I didn't show you the snow, or maybe I didn't apply it. I might have shown it or I didn't apply it, because I know I didn't do a roof, did I? That's what I didn't do. I don't think I did a roof system. Now, you can specify, like for instance, I have 80 pounds per square foot. I have reducible loads, unreducible loads, so on and so forth. So make sure that you're specifying that accordingly. You've got different regions of the floor that have different loads, so make sure you're specifying that. Yes?
What's going to be the difference between storage and unreducible?
I'd have to check. I don't quite remember, but honestly, what I do is I just go with reducible or unreducible and just specify the loads accordingly. I don't remember, though, what the difference is, like how it handles it, but really the big difference for us structural engineers is whether or not it's reduced or not. That's why I always just pick reducible or unreducible. That's a good question. I don't remember, so I don't want to give you the wrong answer. Let's see, did we specify a snow load? We did, so we have a 20 PSF snow load. Okay, so I think let me see, let me go to layout, loads, surface loads. Okay, I think we assigned, let's delete. Okay, so we had assigned the snow or the surface load to the whole building, so the whole floor. Oh, assign that live load to the whole floor. Okay, so we have the live load on the system, and so on and so forth. So we modeled our floor. I'm going to go ahead and model the roof just for the heck of it. Let me go into layout, type. Let's create a roof. Roof, not room. So let's add a roof layout. So here I'm on the roof, so this is the floor and this is the roof. There's nothing there because I haven't assigned a grid and I haven't started assigning member sizes. So let's go to layout, grid. Let's select a grid. I'm also, again, recording this so you all can, play back to your heart's content. So assign that floor plan, and then I'm going to model this not only with joists instead of beams, but I'm also going to specify where my frames are, where my lateral frames are. So let's see, where were they? B and F and 3 and 4. Okay. All right, so here's my floor plan. Let's start off by laying out columns on the grid. So what I might do is I might just put columns everywhere and then go to layout, columns, and delete the ones that are going to be lateral. So that's lateral, that's lateral, that's lateral, and that's lateral. And I just went to layout, columns, and just delete. So now I'm going to add some lateral columns on grid. So that, and that. So if anything, I'm trying to show you how quick it is to actually model this structure. So it's one of those things like if we come back Wednesday and come back Friday and there's no work done, I'm going to be, why? It doesn't take that long. So, yes. That's really up to you. Now, let me say this. I'll give you a few pieces of, or a few minor hints. You need lateral frames along all four directions of the building. The moment, the point when you don't include a lateral resisting element along one direction, wind hits that direction, boom, building falls down. So you need lateral resisting systems everywhere. Now, moment frames and brace frames, I'm not going to tell you which one to use and on which direction. I mean, there's four directions of the building. Each one has a choice. I will go ahead and tell you there are some answers that are more right than others, okay? And I'll go ahead and tell you one of them, okay? For the front of the building, the main entrance of the building, which one do you think you're going to use, moment frame or brace frame? Why? Exactly. Not even just the windows, but the doors, right? I mean, if you're building this structure, you'd like to be able to go into the building. So having a big brace right in front of the door. What's that? Yeah. By saying stay away, stay out, stay away. All right. Layout beams on grid. So what I'm going to do is I'm just going to lay out beams everywhere, and then I'm going to delete the ones and add laterals. So beams, delete by fence, delete those, delete those, delete those, delete those. And then layout, beams, add on grid, lateral beams, bam, 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 bam. Now I'm going to show you something here that will probably be pretty relevant given the structure that you are building, and we're just having some fun with it. So, for instance, if I go to layout, beams, and then add generation, okay, so let's say I'm adding some gravity beams. Let's do 4 spaces per beam. Let's do these 3 bays as beams. Okay, see how they're coming in light blue? They're coming in light blue because we're framing them as just regular old I-beams. Now, I'm going to say that these are going to be regular old beams, but everywhere else they're going to be joists. Okay? Now, the way I'm going to specify that, if you go on the very top, see where it says steel, and I drop that down to steel joists. Now what I'm going to do is I'm going to say, all right, let's put in some steel joists. Let's go to layout, joists, and add generation. Let's add like 5 spaces per beam. And I think you'll see where I'm going with this here in a second. So let's add a bunch of these going down, add a bunch of these going down, these going down, etc. Why am I using beams in these center 3 bays but joists everywhere else? That's where the equipment is and so on and so forth. So what I'm getting at is you can specify where you're going to use joists and where you're going to use beams. You can also specify your different loading scenarios. For instance, I can create a 100 PSF non-reducible live load and just apply that in that little square and then apply a 20 PSF snow load everywhere else or what have you. You see what I mean? So you can specify that accordingly, and I wanted to show you that that's an option. And really the only big thing you got to keep in mind is, when you're drawing your beams, make sure you switch to steel joists. So the joists, those are those open web or open web joists that you see, like Walmart and places like that. So, sound good? I just wanted to show you that's an option. Okay, sound good? All right, so let's do a data check. no warnings, no issues. So save that. And then, we got to go in and we got to assign our decks. So let's have some fun with it. Let's create another decking. Let's say this is a non-composite floor system. We'll call this roof deck. I'm just messing around with it. Let's just say it's 20 PSF. Okay? Let's just say it's 20 PSF for self-weight and just add that. Let's just go with it. So we'll hit OK. So remember, we got to do a slab opening, so we'll do a slab edge. What was our overhang? What was our slab overhang? 6 inches. So 6 inches. Do that along the whole perimeter. Let's lay out slab, deck assign. Let's do that. See where it says framing system? Let's go to non-composite. Add that on the whole floor. So now we got our roof deck on there. And then we need to put our snow. So let's go ahead and put our snow. So let's go to layout, loads, snow loads. Let's put that snow everywhere. Okay, pretty simple, right? All right, so let's save that. Okay, close.
Why wouldn't you put the slab flooring on the beams?
I'm just doing something different. I'm just messing around with it and having a little bit of fun with it. So let's go into beam. Let's design all. Okay. Now, I want to show you a couple things. So let's go to floor 1. Now, I think I showed you that, for instance, if you look right here, you can see all the designs, right? You know, the W18 by 35, there's the 24, and, you know, camber is 1 inch. I showed you that, right? I do want to show you a couple other things. So, for instance, criteria, okay? Steel design codes. Look at this. So we have AISC 36010 ASD, LRFD, so on and so forth. If you're worried about the maple syrup ice, whatever it was, you can throw in the Canadian code. That's the Canadian CSA code, S16. Euro code. I mean, you could really have some fun with this. But we're going to use 36010 LRFD. Let's see what else. Criteria. Deflection criteria. Look at this. So deflection criteria, it's sizing these based off of, you know, post-construction, L over D. See right here where it says L over D. That's a live load deflection limit of L over 360. So you can see post-composite live load. You can have deflection limits during construction, so on and so forth. You could really sort of, you know, tailor this output to whatever it is that you want. I just want to make sure everybody's aware of these, you know, what have yous. Camber. So, for instance, do not camber beams with spans less than what have you. Do not what's the minimum camber? So here it's stating that the minimum camber is listed as 3/4 of an inch. So basically what it's doing is it's computing the dead load deflection, and what it's saying is if you have a dead load deflection that's like 1/4 of an inch, don't bother cambering it. Because, I mean, keep in mind, if you're doing a steel frame, what does it mean to camber it? It means to actually take that beam and bend it. Physically bend it upwards, you know, 3/4 of an inch or what have you. If you have a dead load deflection of like 1/4 of an inch, is it really worth the trouble to bend it upwards 1/4 of an inch? No, it's not. So, for instance, it's stating minimum camber is 0.75 inches, and it's specifying that in increments of 1/4 of an inch. So you could split that up and say, well, I want camber specified to the 1/8 of an inch. So it'll do that. On top of that, it also has a maximum camber listed of 4 inches. So if you picked a really, really slender beam that had adequate strength, but it would need to be cambered like 6 inches, Ram Steel will probably upsize that for fabrication purposes. So you got to keep that in mind as well. All right? Sound good? So there's a lot of things that Ram Steel's doing in the background. I really want everybody to be aware of. Let's see, joists. It's selecting from Steel Joist Institute's standard tables. So for instance, I know what I forgot to do. Let me close this. I forgot to actually assign the roof to the building. So I got to go into story, and I got to add an 8th floor. So let's add an 8th floor, which is actually the roof. Now, I was wondering, like, why didn't the roof get designed? It's because it's not being used. So there's me actually adding the roof to the building. Like if you zoom in, you can kind of see this is going to be tough to see a little bit. You can kind of see right here, you can see there's the joist elements and then there's the beam elements in there. Everybody see that? So there's your open web joist and so on and so forth. So. All right, let me go back to beam. Let me redesign. All right, let me go to roof. There we go. All right. So if you look at the member sizes, so here's the beams that are being used. But if you look here, that's a K series joist, 14 by 1. So y'all know what I'm talking about? Have y'all gone through and seen that in the joist catalog? So those are K series joists, and those are the joist sizes. So on and so forth. Everybody okay on that? Any questions? Okay. There's a couple, let me say a couple things. There are some things that we are ignoring in the grand scheme of things, and I want you all to be aware of this. There are a few more rigorous deflection or structural checks that we're sort of ignoring. For instance, vibration. That's something we really don't talk about a lot in here, but it's something to be said that, yeah, you could have a building that has enough strength and doesn't deflect too much, but if it has unsettling vibrations, sometimes you have to change the design a little bit. You know, have you ever been walking on a bridge, like a bridge with a sidewalk, and there's traffic going on and it does this? It's a little unsettling, a little unnerving. That bridge might have adequate strength and adequate deflection performance, but it might not have adequate vibration performance. So adjusting that design is something that, at least in the real world, you have to consider, but we just don't have time to dig into that. I just wanted you to be aware that that is a thing. All right, without further ado, let me show you columns, and then we'll get into lateral. So column design, let me go ahead and design everything. Okay, again, I think I've shown you all this. You can go into criteria. Again, design codes, we're using 36010. You know, you got Eurocode and Canada and all that stuff. Sign design default, so that's really not going to matter for us because all of our columns are vertical. So this one's going to be really straightforward. Okay, let me go back into the model, the modeler window. Okay, so here's the modeler window. What I want to do is I want to talk a little bit about the lateral system. Okay, now I'm going to start off by looking at this lateral system and this lateral system, the one that's on, I guess, looking at this, maybe the west and east side of the building if up is north. Now, the way I'm going to do this is if you look over here up top, see this is the 3D view, this is the elevation view, and this is the plan mode. The plan mode is grayed out because we are looking at plan mode right now. Okay, so I'm going to look at the elevation view, and I need to pick a frame. Well, what I'm going to do is I'm going to pick this one over here on the left. Bam. Okay, so that is our frame for the structure, the lateral frame. That's the only thing it's going to show on elevation mode because that's the only thing we care about from a structural standpoint is the lateral frame. Okay, now let me zoom out a little bit. So, okay. Well, fine, be difficult. I'll just leave it like that. Okay. What we need to do here is we need to assign some segment or some degree of a lateral frame. Okay? Now, like I said, there's brace frames and there's moment frames. I'm going to show you all braced frames first. Okay? So just like before where you can lay out, you know, columns and beams and slabs and loads and so on and so forth, you can go down here and lay out braces. Okay? Now, there's a few different ways that you can lay out braces. You can design your own braces. You can add standard braces. I'm going to go ahead and add a standard brace because there's a lot of different options. So add standard, okay, and here's your braces, okay. Now we've got, look at the different profiles. We have single diagonal braces going up and to the right, up and to the left. We've got V braces. We've got inverted Vs, which are called chevron braces a lot of the times, X bracing. These are all concentrically braced. In other words, the braces are all designed to meet at a common point. These are eccentrically braced, where there's a little bit of a gap. Eccentrically braced bracing is very common in seismic land because you kind of create like a fuse between those braces. We don't need to worry about that for West Virginia. We're not really worrying so much about seismic braces. What I'm going to do is I'm going to use a chevron brace. So I'm going to use chevron bracing. That's this inverted V. And what I'm going to do for the properties is I'm actually going to change the yield stress to 46. If you pull out your steel manual and you look at the typical yield stresses for tubing, for hollow structural steel tubing, that's what it is. And that's a very common element to use for bracing, like square tubing. It's very, very common. So I'm going to do a fence, and bam. Okay? So everybody see that? So if I go and render the structure, you can now see I've got braces assigned. Everybody see that? Okay. Now I'm going to do the same thing over here on the east side of the building. So let me go into plan view. We'll say, it doesn't really matter, so we'll say okay. Actually, let me go back to modeler. Okay, let's go back to plan view. Now let's do the same thing over here. Layout, braces, assign, add standard, fence, bam. Yes. Special braces if you want to lay out, that's what I'm saying, that's if you want to lay out your own configuration. Like, I'm going to take it and put the brace going this way at this distance and so on and so forth. I would argue that 99 times out of 100 you're never going to need to do that unless you've got some really weird architectural restrictions or you've got seismic stuff to deal with. But in most instances, even if you've got seismic stuff to deal with, there are very standardized seismic systems that you can use, and more often than not, you never need to worry about it. So the program offers you the flexibility, but you're really not ever going to need to. That's a good question. Sound good? Okay. All right. So that's my braces along the west and east sides of the building. For the other sides of the building, I'm going to let me go to plan view right here. So this is my moment frame, and I could put braces everywhere, but I'm not. I'm just going to use a moment frame. The only thing that I have to do on moment frame land is this. Does anybody, what makes a moment frame special? Does anybody remember? Like, I mean, yeah, there's no braces, but how does the frame hold it up if there's no braces? Like, what makes the frame laterally stiff? Anybody remember? So you're right, and basically what we're talking about is the fact that the connections are fixed. These beams that you see here are not pin-pinned. They are fixed into the column. So what we need to do is fix all of these joints, okay? Now the way I'm going to do that, just to keep this simple, is I'm going to go into layout, braces, and instead of assigning braces, I'm going to assign frame fixity. So if you see here on the bottom, see where it says assign frame fixity? Go into that, and there's a couple different things that pop up. So for instance, we have here major axis, minor axis, and torsion. I'd ignore the torsion. That's we're just going to just keep that pen. That's simple. That gets into a whole other can of worms. Minor axis and major axis. It's pretty common in moment frame design to assume that the y-axis is pinned and the major axis, the x-axis, is what we're fixing. Now, if I just left it like this and ran a lateral analysis, this building would fall over, okay? And the reason why is if you're pinning everything, I mean, imagine if this whole frame was just held together with pins, it would be pretty wobbly, right? You've got to fix something, okay? And in moment frame design, what is typical is to fix your major axis. So what I'm going to do is I'm going to fix the major axis, and just to keep this simple, I'm going to fix this everywhere. So fence, and fix that everywhere. So it didn't really change anything from the modeling or from the visual perspective because it didn't add any elements. What I did is I'm assuming that instead of essentially having hinges and pins at all these given joints, no, they're fixed. And that's what keeps the building up. So it might seem like, well, you know, if you're looking at this from an economics perspective, well, gosh, aren't moment frames cheaper because there's less elements? Well, there's less elements, but the connections for those elements are a lot more beefy. So it's a trade-off. So, and that's where your research is going to come into play. So let me go in and finish that on this side. So put that over here. Go to layout, braces, assign frame fixity, fix, fence, bam. And we're done. Is everybody okay with that? Now, this is what you're not going to like, but this is going to make your, I mean, it's going to add a little bit of work, but there's really no other way to really get around this because lateral design in it of itself, in its nature, is really, really complicated. I propose that for a building like this, really the easiest way to design your lateral system is to just make a few guesses as to your member sizes and then to start adjusting accordingly. What I mean by that is this. Let me go back to, let's go to layout, or actually, let me go to my elevation view. Let's go right here. Let's look at this one. So here I've got my braced frame. What I'm going to do is I'm going to handle my braced frame assessment a little differently. What I'm going to do is I'm actually going to assign some member sizes. Okay? So right now, RAM is treating these braces as if they're just lines. What I want to do is say, no. These are 10 by 10 by half-inch thick tubes or what have you. So I'm actually going to assign member sizes to these braces. So I'm going to go to layout. I'm going to go to brace. We'll say assign size. Okay? And so we'll go to rectangular tubing, and let's just pick something. Let's just say, I don't know, 10 by 10 by a half. That sounds good to me. I just guessed that. So we'll fence. We'll assign that everywhere. So if you look at your member sizes, you'll see that your columns and beams are already sized from the design that we did earlier, and now you can see I've actually manually inserted HSS 10 by 10 by halves on all these different braces. And I'm going to do that for the other frame as well. So let me go into elevation on this frame. So here on this frame, you can see that the beams and the columns are already figured out, but not the braces. So I'm going to go in, I'm going to assign those brace sizes. Braces, assign size, fence, bam. The reason why this is going to get a little annoying, it's not going to take too long, but what's going to get a little annoying is that unfortunately, the lateral design for this building is going to be a little iterative. You're going to have to guess a size, monitor your drift. If it's too much, maybe bump your braces up a little bit. If it's too small, bump your braces down a bit, and so on and so forth. Does that make sense? So you're going to have to iterate that a bit, and I'm going to show you how. Okay. Everybody okay with just assigning some brace sizes? Like I said, I just guessed one right off the bat. Just guessed one. Okay. All right. Let me close this. Let me close this. Let me save it. All right. Let me redesign my beams in 3 seconds. Okay. There's my beams designed. There's my columns design. Because every time I do that, like, man, that took us 2 months. You did that in 2 seconds. Where'd you park your car, Dr. Mike? We're not done with this semester. Good luck. Good luck. Oh my goodness. Oh my goodness. All right, I want to show you all something before we get into what I'm about to do here, because I kind of want to really quickly explain how RAM assigns lateral cases, and the only way to do that is to show you a really quick example on the screen. So give me 1 second. Okay. This is going to sound a little weird, but bear with me. Okay? Let's say we're looking at plan view of a building. Okay, plan view of a building. So this is in the helicopter looking down like this. Okay? Now, let's say that our building is nice, pretty neat, rectangular structure. Engineers love it. So it is on. It's running out of ink, though. It is. Okay, so let's say that this is the building, okay, rectangular. Where is the center of mass of this building? Right there, right? Okay, now, this is going to seem a little weird, okay? If I apply a wind load and I'm blowing on the building like this, or so on and so forth, I might resist that lateral load with frames maybe here and here, right? Now, what I'm now going to introduce to you is a term called the center of rigidity. Now, if I've got frames that are equally sized on either side, I propose that the center of rigidity is also right here, right? But what happens if I have like a really strong brace right here and just toothpicks over here, okay? What happens there is I have a little bit of a difference between where my center of mass is and where my center of rigidity is. Does that make sense? Okay, so what happens is when I take a wind and I hit the building, just because of the location of where the center of mass is and where the center of rigidity is, the building's going to twist, whether I want to or not. Now this sound is like, if you're looking at this example, this rectangular building, you're like, why the heck would you put a really strong brace on one side versus another? You'd probably be right. There's no reason to do that. But what my question is, what happens if you have a building that's, like has some floor plan like this, and it's got braces here and here and here and, here and so on and so forth. You might have an instance where the center of mass is like right there and the center of rigidity is like up here, okay? So regardless of where the wind hits the building, it's going to want to twist it. Does that make sense? Everybody okay with that? I'm showing you that because I want you to understand what you're about to see here in a quick second. All right? Yeah. Okay, so here's my RAM frame module. I want to show you a few options, and then when you start to see the load combos spit out, you're going to go, where the heck are all these load combos coming from? Now you'll see here in a second. So let's go to criteria. Let's go to general. So a couple of things. So do y'all remember tau B? Remember that in steel design? So this is where you can tell the frame analysis to assign tau B. Now most of this general criteria stuff really relates to buckling and seismic and things like that, so a lot of this we can sort of ignore right now. But there are a couple things that are worth considering. Diaphragms, we're always going to assume for our purposes that these diaphragms are rigid, and what I mean by that is we're assuming that each of the floors of the building are stiff enough that they can be modeled as really rigid plates. Like if you've got a really flimsy floor system, not only is the building going to want to deflect under load, but each floor is going to want to deflect as well. That's the difference between a rigid diaphragm and a flexible diaphragm. For our purposes, we're just going to keep it simple and say that everything is rigid. Now, I want to go into assigning are going in and looking at loads. So we have gravity loads, we have masses. Let's look at exposure. Okay, so the exposure, that's looking at, this is looking at the outer elements of the building. So if you notice, see how all these minimum and maximum, see how they're listed as half a foot? That's because the slab overhang is 6 inches. Y'all remember that? So you can see where that's coming from. What's that? You can go in and literally just type in. Yeah, you can go in and just type in. Let's see. Looking for something. Loads. Load cases. Here we go. Loads. All right, so I'm going to go into loads, and I'm going to go into load cases. Now, if you notice, there's 2 load cases that are already defined, and that's dead load and the live load. That's from the gravity loads. Okay? Now, let's take a look. So we've got wind, seismic, dynamic. We've got notional loads, which that's, I'll talk about that maybe later, but ignore that for purposes of our discussion. We'll talk about that later. But let's apply a wind load. Okay? Now, we're going to go to ASCE 710, and we'll call this wind effects, and hit add. Now we got a couple things that have popped up. All right. You all remember, first off, these are all in your notes on Blackboard, so anybody can pull this up. But do you all remember in steel design when we started talking about, well, you know, where do snow loads come from? Where do wind loads come from? So on and so forth. Well, first off, we need our wind speed based on our location in the United States. Like for most of the United States, our design speed is around 110, 115 miles per hour, except for the coast. Why is the wind speed higher on the coast? What's that? Well, yeah, that's true, but there's another reason. What do you see out in South Carolina and Florida and Louisiana that we don't see as much in? There we go.
I mean, but hurricanes are an ocean-specific.
Okay. A lot of these factors are going to be held constant. So, for instance, your topographical factor, hold on, pay attention. Your topographical factor, that's if your building is sitting on a really, really tall hill and you can get these like wind speed up effects. We're not going to assume that for our building, so we're just going to take KZT to be 1. Our directionality factor, that's pretty much taken as a constant, is 0.85. Our basic wind speed, I will leave you all to look up what the wind speed is for Huntington, West Virginia. I know you all know how to do that because we've done that in steel design. Y'all done that similarly for snow loads as well. I'm just going to use the value as is. Now, when you hit OK, look what happens. See how, you know, we had dead load and live load, but we've got like, what? Like 12 different wind load cases. The reason why is because you have to consider what's going on. There's load with just the wind on this side of the building, and then just the wind on this side of the building. Then you have wind plus a little bit of torsion. Then you have wind plus a little bit of torsion. Then you've got wind hitting both sides of the building, wind hitting both sides of the building. So if you start doing the math, the number of wind cases that you have to consider can kind of jump up quite a bit based on the geometry of your structure, okay? Now, a lot of times what happens is these don't govern, but you still have to go through and assess them. Luckily, these programs will just sort of do it for you. So I'm going to hit OK, all right? And now that I've got my wind assigned, I'm going to go ahead and perform my analysis. And I'm going to analyze all of them. Bam. Analysis is done. Okay. Now, what I'm going to do, I'm going to go into process. I'm going to go into results. And then what I'm going to do is I'm going to look at deflected shape. Oh, wait. Did I do the wrong? I think I might have clicked the wrong. Results. Deflected shape. There we go. Now, what the deflected shape is doing right here, so first off, it's scaling these deflections up like by a factor of 200. So this is under the dead load, so the frame is deflecting downward, but it looks exaggerated. It's really not that much, okay? Let's take one of the wind load cases. Like, let's take this one. Okay, it looks crazy. Listen to me. Listen to me. The Flash. Let's take that scale factor. Let's move it to a scale factor of 1. That's a little more reasonable, right? Let me animate it.
Yeah, that's not good.
That's a lot, right? Okay, what does that tell you?
We need to do better.
It's not strong enough?
We need more.
You need bigger sections, right? So what you're going to need to do is go into those lateral elevations and assign bigger columns, bigger beams, right? Until those deflections are manageable. That's the load this way. Let's look at that load. Now look at this way. This is on the y-axis. Oh, let me do this. All right? Gravity. So you're just for gravity, so they're not big enough, right? But let me be clear. You don't upsize all of them, just the red ones, just the lateral ones. Now let's look at deflected shape again. I want to look, now look at this, okay? This is the x-axis, and it's moving like crazy, right? That's the x-axis. Now let's look at the y-axis. Hardly moving at all, right? So maybe it's only, for this building, maybe only the x-axis is the one that the sizes need to be bumped up. Maybe the y-axis, maybe these braces are too big. Maybe you need to take those and scale them down a bit. Make sense? Specifically, if you look over here, if you look at reports, right, and you look at story displacements, you can look at each of these story displacements based on the load case, and you can determine what the displacements are. Like, for instance, under wind load case 1, that thing is displacing 75 inches. Now, look, I knew that was going to happen on the x-axis because I just used the gravity columns as are. They're way too slender. You've got to take those and beef them up a bit. But listen to me. This is where the iterative nature comes into play. You have what? They're like W10 by 33s. So take those W10 by 33s and turn them into W10 by 95s or whatever. And now monitor it. And once those values get within acceptable limits, then you know you got your size. Now, if you look at the y-axis, it's only displacing like 2 inches, like 1 inch, so on and so forth. Does that make sense? Now, I'm sure you're asking, well, what's the limit? What's the tolerable drift limit? It's in some of those design guides that I'm going to make you all do some research on. Ugh. Hold on. The student going to grad school went, oh, research. Hello. You go into, okay, so, yeah. It doesn't take that long. Hold on. I told them this in concrete design. I said, if you wait until the last minute, it only takes a minute, right? Did I tell y'all that too? No. All right. Everybody pay attention. So you go into the model window, right? What you can do is click your elevation view, go to like this frame, then you'll go to layout, braces, and then assign size, or beams, assign size, columns, assign size. And it's only going to do your lateral elements, so. Yes? Yes.
Put one here, one here.
It does that.
That's 2 walls.
It does that.
But what if you have one like diagonal wall that?
So you're going to add a whole nother wall to the building?
Instead of having 2 separate walls to resist diagonal loading, what if you just had one diagonal wall so it's less construction?
Well, what about the load going this way? But here, I get what you're saying, but here's the thing. You've got to consider that wind can hit anywhere from 360 degrees. So what I'm saying is put walls here, 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 and here. And what you're saying is do this. It's still 4 walls. You just changed you just changed all their orientations. I would also propose that because those walls are like aligned with the centroid as opposed to perpendicular, they're not going to be as effective. You want them as far away from the centroid as possible. So. All right, hold on before we leave. Are you all good until Wednesday or Friday? You tell me. But it doesn't matter to me, but whatever we come back, we got to have some progress. Yes?
What if our design decking is not in RAM?
You can program one. Yes. You can program the specific parameters, but it should be. Let me stop the recording. So.